And greetings again, everyone. This will be the first part of our 23rd lecture for Math 353. We are still talking here about double integrals over non-rectangular regions. So we thought about the basics of non-rectangular regions. We identified what we would call type 1 and type 2 regions. We thought about how to take integrals over such regions as iterated integrals. Now we are going to think about possibly changing the order of integration. So when our region was rectangular, Fubini's theorem told us that we could change the order of integration freely, just flip things around without any concern. But the process will be slightly more involved here for non-rectangular regions. In particular, at the end of our last lecture, we considered this integral. So with an integrand e to the negative y squared, and D was a region given in this form. We recognized that if we represented D as a type 1 region, the corresponding iterated integral turned out to be impossible. But when we reformulated D as a type 2 region, to which it is equally amicable, then we were able to write down a corresponding iterated integral that proved to be relatively simple. It only took a simple U substitution to compute that integral. So sometimes for regions that can be expressed as either type 1 or type 2, the expression as one of those types might lend itself to nicer integrals. In particular for this problem, when the region was expressed as one type, the corresponding integral was impossible, whereas if the region was expressed as the other type, the corresponding integral was relatively simple. A way that I could have phrased the problem that we considered last time, instead of giving you a description of the region in terms of the three lines that bounded it, I could have handed it to you as the iterated integral over the region, with the region being expressed as type 1. So this is where we landed when we began down the path of computing the problem with the region expressed as a type 1 region, and we realized that this integral was impossible. In particular, the innermost integral cannot be computed. There is no antiderivative of e to the negative y squared with respect to y. So if I am being a sneaky math teacher, I could give you a problem in this form, just given this way, and I could ask you to compute this integral. And it would be your job to recognize that the integral as written is not possible, and that you need to change the order of integration here. This is given as a type 1 region. I know that because it's my x variable that corresponds to the outermost integral, and that is the integral with constant limits of integration. So I'm looking at an expression of a region where my x variable is bounded by two constants. And so it's given here as a type 1 region. If I can recreate the region from the limits of integration that are given, and then re-express that region as the other type of region, then I will be able to rewrite this iterated integral as the other iterated integral. This dy dx integral will be rewritten as a dx dy integral, and perhaps that will help things. At least the fact that I can express them either way gives me another path that I can consider, another suite of tools that open up possibilities for me. So we want to attempt that. We want to change the order of integration, and this is going to require us to first reconstruct the region from the given limits, and that means draw it. So take the limits that were given and draw them out, re-express this region as the other type, as a type 1 or type 2, and then rewrite the new iterated integral. Rewrite this iterated integral, which is a dy dx integral, as the new iterated integral, that being a dx dy integral. Let me be very clear here that you can't just switch around the x and the y and switch around the corresponding limits of integration. That does not work. You do not get the same answer. That's what works for rectangular regions. It does not work for non-rectangular regions. We know this is a non-rectangular region because we have a variable limit of integration in here. If all my limits of integration were constants, we'd be integrating over a rectangle, and Fubini's theorem tells you that you can just switch the order of integration around freely. But for non-rectangular regions, you actually have to go from the limits of integration that are given to the picture of the region, from that picture to the equivalent expression as an iterated integral with the integrals taken in the opposite order. So this is an integral over r, where r is given as type 1. We'll go from there to the picture, then we'll go from there to the integral over r, where r is written as type 2. It is possible to come up with theorems that give you a more algorithmic way to swap the limits of integration, or to change them rather, not just to swap them, but to change the limits of integration without going through the picture. But it's honestly not the best way. It's difficult, and most students who try to come up with some type of algorithm of this kind will get hung up on certain types of problems. So there will be problems that their schema will not work for, and the most reliable and the most intuitively satisfying way, to my mind, is to actually recreate the region from the given limits and then re-express that region as the other type of general region in the plane. So let's look at an example. We'll illustrate this with an example. We will rewrite a more formal outline for how to approach these types of problems, and then we'll do some sample problems. So here's a given problem. I can just hand you this integral, 0 to 1, x squared to 1, root y sine of y, and it's a dy dx. So these are my limits of integration for the y integral, and these are my constant limits for the x integral. I don't know how to proceed. This innermost integral is with respect to y. U sub is not going to be helpful. You're welcome to try it. Integration by parts is going to take a bit more work and is also not going to be helpful. Again, you're welcome to try it. But it's not a great integral. If you know a bit more, if you know about Taylor's series, for instance, and integration of terms, of infinite series, term by term, then there may be some tools in that suite of tools that could be of use to you. But those are beyond the scope of this course. There's not a great way to proceed with this integral given the tools that we have to hand, save possibly for this new idea that we have about reversing the order of integration. So I'm not seeing anything great here. Generally, if I run into problems, I start trying to find side doors, so I'm not able to attack this head on. What is some way that we can transform this into hopefully an easier problem? And that is going to come, or at least we know that there's a chance that this will get better if we reverse the order of integration. So let's take these limits of integration that are given. We do not have to concern ourselves with the integrand for now. We'll let it stand there for a moment. But we'll take the limits of integration for y and x, and we'll try to reconstruct the region that we're actually integrating over here. So this is telling me that x is going from 0 to 1, that's given here, and that y is going from lower bound x squared up to upper bound y equal to 1. So we're going to have y going from x squared up to 1. And I'm going to draw that region. So when I draw these regions, I always take whichever variable gets constant limits of integration first, because that's easy. It's x, so I'm going to come on the x-axis, and I know where x equal to 0 is, that's at the origin, and where x equal to 1 is, that's another dot over here at 1. So x is going to be sliding along that interval from 0 to 1. That's the whole of that story. Always do the easy part first. You might get lucky and die before you get to the hard part. We are not yet dead, so let's think about the hard part, where y is going from x squared up to 1. So this is going from the curve y equal x squared, and that is the famous parabola of great renown here, up to the curve y equal to 1. Y equal to 1 as a curve is the horizontal line y equal to 1. So for every point in this x interval from 0 to 1, my y variable is going from the lower curve up to the upper curve, shown analytically in this expression and geometrically in this picture. So it's this shaded region above the parabola that we're considering here. Very common for students to get thrown off on things of this nature and to end up shading in the wrong region, but the reasoning that I'm going through carefully here for this example should help you to think about these types of problems. Do the easy part first, think about your variable that gets constant bounds, and we'll see one where y gets the constant bounds in a moment here. But for this problem, x gets the constant bounds, so think about those bounds, x going from 0 to 1. You can draw that interval in the x-axis. Draw the two curves that are the bounds for the y variable here, and make sure that the region you shade is going from the lower curve, y equal to x squared, up to that upper curve, y equal to 1. So for every x value in this interval, y starts at y equal to x squared and increases up to y equal to 1. And that's why I've shaded this region and not this narrower region below. So this was given to us as a type 1 region, and we have drawn it. We will now express it as a type 2 region. So as a type 2 region, we've got the same picture here. The points in this region, let me say rather, the smallest y value associated with any point in this region is y equal to 0. So if I let my y values come down here into the lower half of the plane, there is no part of the region that descends that far. The region begins in some sense right here at y equal to 0 and ends at y equal to 1. For values of y greater than 1, there is no point in the region that corresponds to such y values. So y is going from 0 to 1. 0 to 1 is the interval on the y-axis that corresponds perfectly to this region. You might say that the projection of the region onto the y-axis is just the interval from 0 to 1. And so those are my bounds for my y-axis. What's going on with x? So x always slides left to right. The left-hand curve for x is going to be this vertical component of the y-axis, or this vertical interval, some interval on the y-axis. And the y-axis has formula x equal to 0. So we're going to have x going from x equals to 0 over to this curve, which we had written before as y equal to x squared. If I solve that for x as a function of y, it comes out to be x equal to the positive square root of y. And so that's going to be the right-hand curve here. Again, backing up for a moment, we had x squared less than or equal to y here, and that ended up translating into x less than or equal to the square root of y over here. Again, I don't mean to indicate that you can just rearrange things in an automatic kind of way. I have never seen a student do it that way. Well, let me say rather that I have seen students attempt to come up with some kind of automatic translation process and fail quite often. It is definitely the norm that those attempts do not pan out well. And I encourage you to go from the given limits of integration to the picture, and from the picture to the new formulation. So now we have this region R formulated as a type 2 region, and we are able to translate the given iterated integral. So here's the iterated integral that we were first handed. We now recognize that this is just the double integral over this region R, and that R can be equally well expressed as a type 2 region, and the integral over R with R expressed as a type 2 region is given by this iterated integral. So we're going to try to solve this integral now. What's changed is that whereas on the left here my first innermost integral was with respect to y, and my integrand depended on y in complicated ways. I wasn't able to actually find an antiderivative there. Now my innermost integral is with respect to x, and my integral is actually a constant with respect to x, so it will be particularly simple to integrate with respect to x. In fact, we just introduce an extra factor of x, and we're evaluating from x equal to 0 up to x equal to the square root of y. Plugging those values in and simplifying, we end up with a single variable integral that looks like y sine of y. This should be familiar to you because this is one of my canonical examples of integration by parts type integrals. This is a classic example of an integral where integration by parts will allow us to solve the problem. So I always write out my little schema for integration by parts. You may have seen it in terms of u and dv instead. We get to assign what the f prime and the g are. I'm going to let g be y because I would rather be dealing with g prime, which is 1. That means f prime has to be sine, which means that f is the opposite of cosine. Now I'm going to have f times g given here, and then minus the integral of f times g prime, so just negative cosine y times 1. This expression is going to simplify. I get a 0 when y is 0. When y is 1, I just end up with the opposite of cosine of 1. Negative and a negative make a positive. The antiderivative of cosine is sine. Plugging in 1 and 0, and I end up with sine of 1 minus cosine of 1. Sine of 0 being 0, of course, here. So, big picture again, I hand you an integral that can't actually be computed as it stands. It's your job to realize that it might be of benefit to reverse the order of integration. To reverse the order of integration means to take the limits of integration that were given, use those to reconstruct the geometry of the region, re-express the region as the other type, and rewrite this integral as the other iterated integral with the order of integration reversed, and then hopefully solve. So here is that process summarized. You're starting with a description of the region as either type 1 or type 2, and that description may have been handed to you as the limits of integration of an iterated integral that you were asked to compute. Use the description to draw the region. I encourage you to draw pictures throughout this course. It is a very visual course, but especially for this type of problem, it is, if not quite a necessity, it is certainly the safest way to do these problems. And especially given the fact that you'll have plenty of time for exam questions from now until the end of the course, I definitely encourage you to draw these regions. Then redescribe the region as the other type. If it was given as type 1, redescribe it as type 2, and vice versa. And set up your new iterated integral with new limits of integration given by this new description as the other type of region. So let's have you folks do some of these. So here is an iterated integral that I'm handing you. We're going dy dx integral where x is going from 0 to 1 and y is going from x up to 1, sine of y squared. Give that some thought. Feel free to look back at your examples or notes, look things up on the internet. If you're working with somebody else, feel free to collaborate, and we'll reconvene in a moment to discuss this problem. Alright, so taking a look at the solution here, a 0th step perhaps that was not included in our list of steps to approach problems of this type that we just gave is to realize that the integral as it stands is not possible. So generally, if you're handed an iterated integral, if you're able to proceed straight away, then do so. If a head-on approach is going to work, then that's great. Go ahead and do it. Those are generally simpler problems. But if you're given an iterated integral of this kind, like the one that we've just been given, and you're not able to proceed in a straightforward way, you're not able to compute this innermost integral, then perhaps you want to change the order of integration. Right? This speaks again to the metagame of a math class. You have different techniques, but how do you know when to apply each of the techniques? So if a straightforward approach will work, employ it. If it does not work, then this technique offers you another possible path. And I am not able to make headway on this innermost integral. I can't find an antiderivative. Some folks will try to write something like 1 over 2y, the opposite of cosine y squared or something of that nature, but that is not actually an antiderivative. They're trying to effectively just do the same thing that they would do like with x to the 7. They would write it as 1 over 8, x to the 8. But it doesn't work. If you differentiate that expression, the quotient rule is going to involve something, or is going to result in something more complicated than this integrand. You will not get back your original integrand. If ever you think you've taken an antiderivative, differentiate it and see if you get back the original expression. You will not in this case. So I am not able to make headway on this integral as it stands, and we are going to attempt to reverse the order of integration. So we're going to give a name to the region R, and here R is given by x going from 0 to 1 and y going from x up to 1. I'm taking that directly from these limits of integration. X is going from 0 to 1, y is going from x up to 1. That's a type 1 region because it is my first variable x that has constant bounds. So first variable type 1 region. We're going to draw this region now. So x is going from 0 to 1. That's the easy part. I draw the x-axis and I draw dots at 0 and 1. And now for each of those x values, y was going from y equal to x up to y equal to 1. So I can draw the curve y equal to x. It's here a line, a very non-curvy curve. And I can draw the curve y equal to 1. Again, it's a straight horizontal line here. Y is going from the lower curve up to the upper curve. So it's this upper triangular region, this northwestern triangle here, not the southeastern. And questions at this point are more than welcome. So if you have questions about this technique, please let me know. I'll be happy to talk more to you about this in office hours. It is a common place for students to get confused and to make some mistakes. But all I'm doing is walking through these, and I'm reconstructing the region from the most basic piece of information that I've given that's easiest to interpret, the constant bounds for one of my variables, and then thinking about the more complicated information afterwards, where we're going from y equal to x to y equal to 1 here. So this is the region, and this is it expressed as a type 1 region. We're going to redescribe this as a type 2 region now. So what should be the constant bounds for y? Type 2 regions have constant bounds for y, and I can see that those should be from 0, the smallest value for y associated with any point in the region, up to y equal to 1, the largest value for y associated with any point in this region. So y is going from 0 to 1. For each of those y values, as y slides up this interval from 0 to 1, we'll have our x variable going from this left-hand curve over to this right-hand curve. So x is going to go from the straight curve on the left to the slanted curve on the right. We'll go left to right, and we'll come back and increment y up a little bit, and we'll go left to right again, and so forth. So this vertical line here is the y-axis, which is given by x equal to 0. This sloped line was described as y equal to x before. We can write that equally well as x equal to y. So I've got x going from x equal to 0 over to x equal to y now. And those bounds for my two variables in the description of this region as a type 2 region are going to be the limits of integration for my new iterated integral. So here's the problem we were handed. We are repackaging this iterated integral into a double integral over the region R, and then we're redescribing R as a type 2 region in the plane to write its double integral as a dx dy iterated integral. If you just wrote that this equaled this, I would be fine with that. If you skipped the expression as an abstract double integral, that's okay. But I am trying to illustrate what's going on here. We're starting with an iterated integral that's been given. We're reconceptualizing that as a double integral over a geometric region, and we're re-expressing that geometric region with the alternative analytic description of such a region from type 1 here to type 2. And now we can proceed. Again, our integrand depends only on y, and the innermost integral is with respect to x, so that makes for an easy first integral. We just pick up a factor of x. It's like integrating 7 and getting 7x. This x value is going from 0 to y. It simplifies down to y sine y squared. This is a classic u-sub problem. I've got a two-factor integrand. One of those factors is a composition of functions, and the inner function of that composition has derivative essentially equal to the other factor. There's some constant multiples that have to be dealt with, but that's why we pick up this factor of 1/2 outside. So integral of sine of u is simple. That's just the opposite of cosine. And then I return to my original variable name before I plug in limits of integration. That is my preference. You could solve for u of 0 and u of 1 and stick with u if you like. But we end up with 1/2 times the quantity 1 minus cosine of 1. Let's do another sample problem. So here's yet another problem. I am handing you this iterated integral. It is not an integral over a rectangular region because we have a non-constant limit of integration. And I'm asking you to solve this. So go ahead and pause the video and give that a shot. Use whatever means you would like, and we will reconvene momentarily. Alright, so let's have a look at this. I am not able to make progress on this innermost integral. The integrand is crazy, e to the negative x cubed. It's an integral with respect to x. I can't write down an antiderivative. If you think you have written down an antiderivative, I invite you to differentiate it and make sure that you get back to your integrand. I would be surprised if you had such a one. I don't actually know for a fact that it's theoretically impossible for this one, but I suspect that it is. I know it's theoretically impossible for very similar integrands. So this looks bad. Maybe reversing the order of integration will help. And that's exactly my thought process. If I come up against a problem that looks unreasonably nasty, then I start to think about ways that might make it easier, and reversing the order of integration could possibly make this easier. So I'm going to take the limits of integration that were given, and I'm going to reconstruct the region. We had y going from 0 to 1, and x going from root y up to 1. This is a type 2 region because it's the second variable that gets constant limits. We are going to draw it now. So y going from 0 to 1, I draw the dots 0 and 1 on the y-axis. That's easy enough. So y is going to slide from 0 up to 1. And then my x values are going to be going from a left-hand curve, x equal to the square root of y. And I make note that x equal to the square root of y is more commonly written as y equal to x squared. These aren't exactly the same as we discussed last time. These are only x equal to the square root of y is the right-hand side of the expression that we usually draw, y equal to x squared. Y equal to x squared is a parabola with two halves. If I write x equal to the square root of y, I only want the half of that where x is positive. Square root always returns a positive, so x is a positive number here. So I'm looking at the right-hand side of that parabola, the famous parabola. So x equal to the square root of y looks like this. You can also note that if I were to reflect the graph across the 45-degree angle, it would look like the square root function that we're used to. That moves up and kind of tapers off and levels out a little bit. So that's that curve. That's the left-hand curve for x. The right-hand curve for x is x equal to 1. X equal to 1 is a vertical line that intersects the x-axis at point 1. So we've got x moving from the left-hand curve to the right-hand curve. That's why I have sketched in, shaded in this skinnier region below the parabola here, not the larger region above it. So y is going from 0 to 1. For each value of y, x is going from the left-hand curve, x equal to root y, over to the right-hand curve, x equal to 1. That's the region. And this is critical. If you don't get this part right, the problem's not going to work. And generally, the computations of these integrals are not the hard part for these problems. The hard part is managing to switch the limits of integration, rather the order of integration, successfully. So this would be, were you to have such a problem on a test, this process would be worth a significant amount of the points, and we definitely want to make sure that people are comfortable with these. So if you didn't get this right, feel free to stop by office hours. If you're not understanding what I'm saying, we can talk more about it, and you will certainly have some problems of this type on our homework that goes up on Friday. So now that we have a picture of this region, we can re-express it as a type 1 region. So trying to think about this as a type 1 region, for a type 1 region, it is my x variable that's going to go from some constant to some other constant. And so I got to think about what interval here on the x-axis perfectly characterizes this region. You might say, what is the projection of this region onto the x-axis? If I were to take the whole region and collapse it all straight down onto the x-axis, what would that interval look like that resulted? And it's going to go from 0 here out to 1. Saying it yet one more way is to say that 0 is the smallest x component for any point in this region, and 1 is the largest x value associated with any point in this region. So x is going from 0 to 1, and we have that here. Y is gonna, to get the same region, we're gonna need y to go from the x-axis up to the parabola. So I'm gonna have my y values, x is gonna slide from 0 to 1. For each point in that interval, my y value should be going from this bottom curve up to the top curve. So from the x-axis up to the parabola, y equal to x squared here, which is why I've got y equal to 0 as the bottom curve, that is the x-axis, and y equal to x squared, our parabola, as the top curve. And this is the expression of that region as a type 1 region. This is our new characterization. So our given characterization from there to the picture, and from the picture to our new characterization. Now we can reverse the order of integration. This is the iterated integral that was given. I repackage these limits into a double integral over the geometric region R. I re-express R as a type 1 region. Now we'll have a dy dx iterated integral of this type. That should be an x cubed right there. This is a typo. My apologies, folks. But right there, we should have a negative x cubed. And so now we are going to be going 0 to 1, 0 up to x squared, e to the negative x cubed, dy dx. The integrand here is constant with respect to y, so I just introduce a factor of y. I evaluate at the endpoints, and I end up with x squared e to the negative x cubed dx. Again, this is a classic u-sub problem. Here's my composition. Here's the inner function. The derivative of that inner function is, up to a constant, the other factor at the top level of my integrand. So performing the u substitution, and we come to this expression for the answer. And that is going to conclude our work on double integrals in what we will learn shortly are called Cartesian coordinates. So all this xy stuff, where we've got the standard xy grid, our way of thinking about the plane, that is known as Cartesian coordinates, and we are going to now loosen that way of thinking and begin to express the plane in non-Cartesian coordinates. In particular, we're going to start thinking about polar coordinates. So, as always, questions are welcome. Thank you, folks.